So this week we are going to be talking about electronegativity and polar molecules. And so as we're doing that today, it may be good for you to take out a piece of paper. You may want to take some notes or draw some things as we are going through this. So first thing I want to touch base on is remind you that when we have a molecule, like when two hydrogen atoms, make a covalent bond, and of course we can tell that this is a covalent bond because if we look at the hydrogen atoms, we can see that they are sharing electrons right here. So there's our shared pair of electrons. One of the ways that we represent that is with a line in between. Remember, each line is those two shared electrons. So my question to you is, if they've made this covalent bond and they're sharing these electrons, how are they sharing those electrons? We ideally think that these electrons are going to be moving around both hydrogen atoms, but do they do that equally? And the answer is, in this case, yes, but not in all cases. And that of how electrons are shared and electronegativity. So if we take a look at H and O can do the same thing to share electrons. So this hydrogen here has one electron here that it's sharing with oxygen, as you can see right there. And this oxygen here has one electron that it's sharing with hydrogen here to make this covalent bond. Of course, that wouldn't be all because that wouldn't give oxygen an octet. So we could draw a line between them to show that pair of shared electrons, but they're not going to be shared evenly. Oxygen is going to take these electrons that are being shared, and oxygen is an electron hog. The term for electron hogs is electronegativity. So oxygen is going to take these two electrons, the one from hydrogen and the one from itself, and it's going to pull those two electrons closer to this oxygen atom. And so these electrons are going to spend way more time around oxygen and a little tiny bit of time around hydrogen. And that's because oxygen is more electronegative. And so this idea of being electronegative is actually a scale of 0 to 4. And it's very easy to figure this out. And so let me show you how you can figure this out. This is a table of electronegativity. And so on this table of electronegativity, you can just look at each atom and then the numerical value there, it tells us how electronegative the atom is. So if we take a look at hydrogen and oxygen that we were just talking about, and you can see I'm going to run out of room here. If we look at hydrogen and oxygen, you can see their electronegativity. And so what we do is mathematically, we take the electronegativity of each and we subtract them. And so as you're taking a look at that, you can say, wow, that's a difference of 1.4. That's a fairly large electronegativity difference. So in our last example, we had an electronegativity difference of 1.4. And so if we look at this chart, it goes from 0 to 3.5. So I'm going to estimate that about 1.4 is here. And then that tells us what type of sharing we've got. So when electrons are shared unevenly, we have what's called a polar covalent bond. If electrons are shared evenly, and this sometimes is a little confusing because when electrons are shared evenly, it's a nonpolar covalent bond. So again, shared evenly, nonpolar covalent, and that's something you may want to make a note of or snap this picture of this little diagram right here. And not shared evenly is polar. So you're going to want to keep that in mind as we're talking about these molecules today. So let's take a look at this molecule right here. Obviously, we have carbon and sulfur. So if you wanted to write the formula for this, it would be CS2, 2 atoms of sulfur and 1 of carbon. And obviously, we've got double bonds here, so that's 4 electrons being shared. Sometimes I just abbreviate valence electrons as VE. So 4 valence electrons being shared. But how are they being shared is what we're going to attempt to figure out. And so you would have to look at the table of electronegativity that we did earlier. And I just happen to already have written that down so that we can take a look at it. And our table of electronegativity tells us that carbon's electronegativity is 2.5, whereas sulfur is also 2.5. So there's our electronegativities. So how are these sharing electrons? These electrons that we have here, evenly or not evenly? So if you said evenly, you are exactly right. So remember that sharing evenly means this would be non-polar covalent. Sharing evenly. Now, obviously, the other thing we're going to be taking a look at next is the shape. The shape of the molecule will also affect the entire molecule's polarity, what we call polarity. And hopefully, if you're taking a look at this molecule, we can just review. The shape of this molecule is linear. It is a straight line, 180 degrees between the atoms. And here's another one to take a look at. Now, you probably don't know what molecule this is because we haven't been in school to build any, and so I built this one for us. This is fluorine, and I'll write it in black, and this is hydrogen. So if you were drawing this molecule, of course, we know that hydrogen has 1 valence electron. Of course, fluorine has 7. So that's a total of 8 valence electrons. We put in 1 bond. Hydrogen is good now. And we give the remaining 6 electrons. After we put in our bond, we give the remaining 6 electrons to fluorine. And now each atom is satisfied with the number of electrons it has. So how are these atoms sharing their electrons? Well, let's locate fluorine. This is our table of electronegativity that we saw earlier. And let's locate hydrogen. So again, we're just looking at the difference between the electronegativities. Fluorine is the most electronegative atom on our periodic table with an electronegativity of 4. If we subtract hydrogen's electronegativity, we've got a difference of 1.9. Wow, that is a big difference. And so what does that tell us? That tells us that these shared electrons that we drew here in pink, that those shared electrons are really spending more time closer to fluorine. So I'm going to draw them way over here. They're closer to fluorine than hydrogen. Now, what you've got to remember is that these electrons, as they slide this way, they take their negative charge with them. So that's going to make this end of our molecule a little bit negative, leaving the hydrogen side a little bit positive. And this Greek letter tells us that partial, not completely positive, not completely negative, not like an ionic bond, but partially positive for the hydrogen end and partially negative for the fluoride end. Now, if we take a look at the shape of this molecule, you can see that the shape of this molecule allows us to have one charge at one end of the molecule and a different charge at the other end of the molecule. So not only is this going to be a polar bond, but this is also going to be a polar molecule. So how did we figure that out? We figured that out first by looking at the bond and then looking at the shape. Did the shape allow us to have one end of the molecule that had one charge and another end of the molecule that had another charge? Let's go ahead and do another one. All right, now once again, like I said, you probably don't know this atom because we haven't been in school to build them. This is O. This is the oxygen in the air that we're breathing in. We call it O2. We've got a double bond here. So we've got 4 shared electrons. And then there's going to be lone pairs of electrons over here on each oxygen atom. Okay, but what we're interested in today is how are these electrons being shared? So what do? We need to look at our table of electronegativity, and we can see that oxygen has an electronegativity of 3.5. The other oxygen atom has an electronegativity of 3.5 since they're the same atom. That's a difference of 0. So if you look back at our chart, anything less than a difference of 0.5 means they're sharing evenly. So these electrons are in fact spending equal amounts of time around each atom. And so we would call this nonpolar. So we didn't even have to look at this molecule shape because we already figured it's a nonpolar bond. A nonpolar bond is going to mean a nonpolar molecule. These electrons are spending even time around each atom. Of course, you do know the shape of this molecule, I'm sure. This is a linear molecule. Both atoms are in a straight line with one another. Here we go. This is CO2. So again, here are our oxygen atoms. In the middle, in blue, usually it's shown in black, but in this case it's in blue. Here's our carbon atom. So if you were going to draw a Lewis dot structure for this, that's super easy to do. Carbon, of course, has 4 valence electrons. Oxygen, each oxygen has 6, and you've got 2 oxygens. And so we've got a total of 16 valence electrons. So you remember you put those in as bonds first, and then show the electrons around. And as I'm doing that, you can see that carbon would not get an octet. So after I've done that, I would move 2 of those electrons from oxygen over. So let me see if I can move those 2 electrons from oxygen over. There we go. So we're going to get 2 electrons, and they're not going to let me do that. We're going to move 2 of these electrons from oxygen over here to be our double bond. So let's take a look at how they're sharing electrons. So once again, on our periodic table, we need to locate oxygen. We need to locate carbon. We can see that carbon's electronegativity is 2.5. Oxygen is 3.5. So if we do the difference there, we've got a difference of 1. So anything, again, between above 0.5 means that it is a polar bond. So as we're looking at these electrons that look like they're right in between carbon and oxygen, these electrons are actually going to be spending more time over here closer to the oxygen atoms, to each oxygen atom. And so what's going to happen to that oxygen end of the molecule? As those electrons move closer towards it, this end of our molecule is going to become a little bit negative. Wow. So that means that we have negatives at each end of this molecule. So we do have a polar bond, but because of our linear shape here, and the electrons being pulled towards the outside, this is going to be a non-polar molecule. And that's what we are trying to recognize, polar molecules versus non-polar molecules. So once again, those steps are to look at the bonds, determine if the bonds are polar or not polar, then look at the shape and figure out if the shape allows it to be polar. Another thing that you can do is if you draw an arrow where the electrons are being pulled, if the two arrows cancel themselves out, that would also tell you that it's nonpolar. All right. Now, like I said, once again, I'm sure you won't know this one. This is nitrogen. And around our nitrogen, we have 3 hydrogen atoms. So our formula here will be NH3. Now, of course, let's take a look at the shape of this molecule. I'm hoping that you can see that our shape is trigonal, pyramidal. You can see that it's poofed up a little bit like a pyramid shape. It's also triangular, so tri is that triangular shape. So there's our shape. And like I said, I'm hoping that you do know those. Now that we've looked at our shape, let's look at our bonds. So there's nitrogen. Let's find hydrogen. So we're just looking at even though we have 3 hydrogens, we're just looking at the electronegativity of nitrogen compared to hydrogen. So of course nitrogen is 3.0. Let's find the difference between hydrogen, which is 2.1. So if we take a look at that, that's going to give us 0.9. 0.9, of course, is greater than 0.5. So that tells us that these electrons are not going to be shared equally. So if we take a look at this atom, who's pulling on the electrons more? The more electronegative atom. So these electrons that look like they're shared between these are actually going to be pulled up towards the top here of this nitrogen atom, which is, if we looked at this molecule from the side, and I couldn't get a great picture from the side, it would kind of look like this. And so you can see that those electrons being pulled up towards the nitrogen, that's in every direction. So these arrows are not canceling each other out. So that's going to make the nitrogen end of this molecule a little bit negative, leaving the hydrogen end a little bit positive. So with a polar bond and the shape allowing us to separate the charges makes it a polar molecule. So one of the things that I think about when I'm thinking about these polar molecules is the Earth. We have 2 different poles. We have the North Pole and we have the South Pole. Both are very different. All right, here you go. This is a great molecule. This, again, in red is oxygen, as always. In white is hydrogen. And so let's take a look at this one. Of course, our shape here is bent. This is a bent shape. We can see the electrons that are being shared here and here. So one from hydrogen, one from oxygen on each side. Our formula, of course, H2O, because we have 2 hydrogens, 1 oxygen. So how are those electrons being shared? And does the shape allow us to have different poles? You may want to pause this and see if you can figure that out. Now that you've figured that out, let's take a look at oxygen. Of course, electronegativity of 3.5. Hydrogen, electronegativity of 2.1. So if we do the difference here, 3.5 for oxygen minus 2.1 for hydrogen, we're going to get 1.4. Obviously, 1.4 is greater than 0.5. So that means that these electrons that we saw earlier that we said were being shared between them, oxygen is more electronegative. It's an electron hog. So those electrons are actually going to be pulled closer to oxygen. They're going to take their negative charge with them. So that will make this end of our molecule a little bit negative. This end will be a little bit positive. And so this bent shape also lends itself, as you can see, our electrons being pulled this direction. Oh, and I probably should have shown that other arrow going like this. You can see those 2 arrows are not canceling each other out. They're just pulling those electrons. So this is going to be a polar molecule. show these polar molecules like this right here. As you can see, we often show them in color, where you can see the more electronegative atom here, the oxygen, being shown more in red with this partial negative charge, and the hydrogen end being shown in blue like it's cool, sort of showing a different poles, if you will, or like a magnet with a north pole and a south pole, is how we often show these molecules. All right, the next one for you to do, CCl4. So if we just give you CCl4, can you figure out what does the molecule look like? What shape is it? How are the electrons being shared to make it a polar or a nonpolar molecule? So this would be a great time for you to stop the video and try this on your own. And I'm going to go ahead and do this one as well. So I'm going to start at the very beginning for this one. I'm going to look at the valence electrons, because obviously I have C, which has 4 valence electrons, and then I have 4 Cl's. That's what that tells me. Each one was 7 valence electrons. So that's going to be 28, 32 valence electrons. So I'm going to have to look at what this looks like, this molecule, to better understand it. So I'm going to determine that C is my central atom. And I'm going to go ahead and draw bonds and put my Cl's all around. Nature tends towards symmetry, so we've got 4 of them, so that's why we would put 1 on each side. So now I put in 8 bonds. So now I need to subtract 8 from 32. So that's going to give me 24 electrons left. So let's see. 2, 4, 6, 8, 10. So let me see if I can get each atom with an octet, because that's what each atom wants, is 8 valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Done. All 24 electrons are in there. So I can see now I've got these shared electrons. How are they sharing those electrons? Well, if you're thinking, oh, in order to do that, you need to look at the electronegativity, you are exactly right. I just so happen to have my table of electronegativity, and I can see that carbon's electronegativity, again, is 2.5. And I can see chlorine's electronegativity is 3.2. So to subtract these, I'm going to have to do a little bit of borrowing. 12 minus 0.7. 0.7, of course, is greater than 0.5. So these electrons that look like they were shared in between, who's the electron hog? Chlorine. So these electrons that we said were being shared in between are actually going to be moving closer to chlorine than to carbon. And so if we take a look, as we watch these being pulled this direction and that direction, notice our arrows here. You can see that our arrows are canceling each other out. So the shape of this molecule is going to cancel out the pull of those electrons. So this is going to be a non-polar molecule. So did you figure that out? Were you correct? I hope. And so here's another picture of what this would look like. This molecule, if we were taking a look at it, of course it is a tetrahedral shape. So now I hope that you know all about polar molecules. That should be an O. And how you can use the shape and electronegativity to determine if a molecule is polar or not.